Okay, welcome to the last part of Objective 1 for Module 5. So this particular module, we're going to look at the different sources of errors and bias in GPS. So like I mentioned, this is not an easy process to be able to correct for everything. There's errors in the atmosphere. There's something called multipath. We have satellite geometry that can cause problems. We have clocks that can cause problems. We have the orbits themselves causing problems. We have receiver clocks that are causing problems. There's also noise, like electronic noise, in receivers, so that can also cause problems. And then users themselves also cause problems. So there's quite a bit that can happen here. So this is a relatively large talk about these errors, but they're not. We're not going to go fully into them, and especially not the math that kind of comes with it. So if you want to go through and try to find your own definitions of each of these and kind of describe them in advance of finishing up this lecture, then I suggest doing that, and then it gives you a chance to go through and see how it matches with what I'm doing. So go ahead, go do that. Come pause me now, and then come back. So let's start with the first one. Let's start with atmospheric errors that we can, and atmospheric conditions. So the atmosphere contains different amounts of water, dust, other particles, lots of stuff that can interfere with the GPS signal. Our atmosphere is not perfectly transparent. We can have all kinds of stuff that happen and can affect the signal. It's not that it blocks it, but it can cause it to bend, called refraction. It can lose energy, like absorption. It can scatter away and then scatter around within the atmosphere, which is adding more error. So there's lots that can kind of go on. And then we have two major components that really of the atmosphere that really affect it, and the first one's the ionosphere, and the other one is the troposphere. So both of those have the greatest effects on it. So the ionosphere, it deals with the speed of light. So it has these charged particles that can slow down and speed up different parts of the electrical code, a pseudo-random code. So you can see here it mentions the charged particles slow down the code that's with the signal, but it speeds up the carrier signal. So we won't get into the electrical engineering side of that, but if you can imagine that there's two together, one has a bunch of information on it, the other one says, hey, just come along with me, and one's speeding up and the other one's slowing down, then you end up with some real issues that come with that. So it's just because the ionosphere is charged. It's ion, which is the first one, so it has charged particles that are there. So because of that, we have the time that is affected, and therefore we end up with an incorrect distance measurement through the ionosphere errors. The other one is the troposphere. So now this slows down the phases of the signal, which is just like the wave, the component of the wave that is in the imaginary part, if you want to think of it in terms of electrical engineering. But it's just like really where that bump is, like where the wave kind of peaks and the valleys of that wave that gets slowed down. So because of that, well, first of all, it's impossible to remove the ionospheric effect. We can minimize it though. It says that it cannot be removed using dual frequency. It actually improves it, improves the tropospheric, like it gets rid of the error better than the single frequency. It's way worse with the single frequency, so I'm not sure why that is stated there. But anyway, moving on. The troposphere removal, how we do that is it measures the water vapor. We can measure the temperature and pressure throughout the atmosphere, and then we apply a mathematical model to compute the delay. So that tells you that water vapor, for example, that varies everywhere, right? Like, you start in Calgary. Calgary has different water vapor, like in the north versus the south. So it doesn't really take much. It's very local. And so then same with temperature. You start at one house and versus the other, and the pressure, it depends on elevation, and you've got like weather systems that come through. So all of these things are very local and they change very rapidly. So all we can do is our best to try to get that information and then apply some sort of math to get the delay. The second, or not second, I guess the second one, because we talked about atmospheres one. The second one would be the multipath. And so what happens when we send out a signal and we're trying to get it to, like, for example, this car, we're going to have some unaffected signals that are going to go straight down. Now, if we have tall reflective buildings are really bad, especially with glass, then we're going to have signals that the signal diverges, right, from the system. And it gets bigger and bigger. And then some of it's going to reflect off the building and go to my receiver. That is what we call multipath. So it's kind of bouncing off. It's changing the pathway of the signal. So when this receiver gets that information, it says, oh, wait, actually, I'm over here. No, I'm actually over here because the path is longer than what it's supposed to be. So highly reflective surfaces are a big problem with multipath. Then the next error is geometry. So this is satellite geometry. So there's two levels of accuracy. There's surveying accuracy and there is mapping accuracy. And so it doesn't go into a lot of detail about that. Mapping is going to have a lower accuracy than the surveying accuracy because we can include the mapping with like the user component. So the geometry has actually got a special measure. And we call it dilution of precision. So it is pretty much exactly what you can imagine. So if you think if I'm going to dilute juice, for example, I'm going to add more water and it's going to expand it out, right? So you're going to have more and more water. There's going to be less flavor of the juice. So then the taste of it might be distorted. So with dilution of precision, that's exactly what I'm doing. I'm taking the precision of my measurement and I'm diluting it so that the error is actually larger than what it was before. So, or what it could be. So the satellite geometry, this is how the satellites are placed above. Ideally, you would have a perfect, like, everything would be an equilateral triangle. All four of them would make these perfect triangles. They're directly above. They're equally distributed across the entire sky. That would be textbook ideal. That never happens. So we need to have some sort of way to measure it, and so that we can make some predictions as to what that's going to look like. So there's a lot of there's like 4 major DOP values, so dilution of precision. The first one is the PDOP, which is position dilution of precision. And we can break that down into horizontal and vertical. So the HDOP and VDOP. HDOP is looking at just the X and Y on the surface of the Earth. Vertical is looking at the elevation and only the elevation. That's the only one that it looks at. And PDOP consists of all that. So if the overall PDOP is HDOP and VDOP, so it looks at the whole precision of the position. And there is also TDOP, which is timing dilution of precision. And there's GDOP, which is the geometric dilution of precision. And geometric dilution of precision includes VDOP, HDOP, and TDOP. So it gets all of them together in one. So if you're trying to get a position, ideally you want to be like directly underneath the satellites and like right in the middle of all of them. And so you want to have as much of a grid above you as possible, like I mentioned. So it states here that satellites should be as low on the horizon as possible. So the elevation of satellites above the position is 0. I don't really understand what they're trying to say there, but I'm going to state that you don't want the satellites super low because there's so much atmosphere for it to go through that as it goes like through the entire atmosphere, it's going to be, you're going to end up with higher errors because of the troposphere than you are going to be worried about dilution of precision. So what you want is the satellites to be above about 10 to 15 degrees above like the horizon plane. And then you want them evenly distributed around. So if you have 4 of them, you want them to try to make equilateral triangles above you. So I'm not sure what this means, but we do not want the satellites to be low because there's just too much there, too much atmosphere to go through. So if you have one satellite directly above you and you have one a little bit lower, then you're going to have a better minimization of that error. And the elevation is more difficult to establish because like the elevation of where you're standing, and it's just because of the fact that it's never going to be in a perfect orientation. And that is the position that is a little bit harder to try to capture. I know it's only one value, but we're dealing with a surface that's curved, and then we're dealing with curved orbits at different angles. So in the math, once you do all the math with it, it turns out that one's the hardest one to try to get. Like, it's just really difficult. And because of the fact that you can't go to the side of where it is, like you can't go below you, right? So everything's above you and it's like a plane above you. So it makes it a little bit harder to get that elevation. But it's not a huge problem. So it is worse, but it's directly correlated with everything else as well. So if you have like a relatively good P-DOP, like, or just an H-DOP, then the V-DOP is going to be improved as well. So here's an example. We have my receiver and all my satellites are at one clustered all together on one side. I'm going to end up with a bad DOP, right? So the DOP value is actually going to be very high. So remember that it's dilution. So it's how much dilution of my error, like of that precision, of the not accuracy, but precision that I have. So the higher the value, the worse off it is. It's really like, how bad is it? If it's really high, then it's really bad. Then if you were to have everything kind of built above you like this, and you're right in the center, then I'm going to have good DOP values. And so therefore it's going to be lower. So another thing that can affect the DOP values is visibility. So if you go downtown Calgary, for example, or downtown whatever city you're in, and there's tall buildings and you're on the ground, you're going to lose a lot of sky. And that signal is not going to make it to you. So you can have a lot of problems with that, and that reduces the number of satellites you're going to see. It's going to change the geometry as to which satellites you're going to see and where they are with respect to you. So the DOP values are definitely going to be affected based on those obstacles. So some typical obstacles you'll see is trees, buildings, mountains, a body. So if you're standing in the way, that's often an issue, especially if you're dealing with a handheld GPS. I don't suggest running around with it above your head. Like, just, try your best to just not be like, hold it out a little bit so that you're not a complete boundary to it. If you have a vehicle and you park your vehicle beside it, it's going to affect the visibility as well. You can't go inside a building and use GPS. It can kind of get a signal, but it's not a reliable signal. The radio frequencies are not high enough to pass through the, like, whatever it is in the ceiling, whatever materials it is. It's not a powerful signal. So it's really hard for it to give you an accurate measure. Okay, so another error is the clocks. So there's atomic clocks can have some errors because even though they're super high quality and super expensive, they can have errors. Everything has errors. So when these clocks have errors and they show that they're having errors, then the master control system can help with adjusting it. But you can see that here it says that when you combine the clocks on the satellite with the master control clocks, then you end up with like 10 superior atomic clocks. Like, we just keep combining it. So this redundancy is going to help reduce that. So the ground stations, they collect the errors and the drifts of the clocks, and then it sends back the information. It says, hey, satellite, correct your clock, and the satellite will do that, and then it'll send down a message saying this is the actual time. Then for orbits, which is the next error, the satellites can deviate from their intended orbit, and it can be caused by all kinds of things. Like, yes, we have Kepler's laws, and we really don't have friction or anything happening there. It's not like being driven with a steering wheel. So there's just, solar winds can move it around. There can be all kinds of stuff that happen. So this, if you move the satellite, because the satellite's not where it says it's going to be, you're going to end up with an error in your position. And the corrections are applied by the ground control segment. Again, they're kind of watching them, trying to make sure it's there. And they're transmitted by the satellite in each signal. And then they can say, hey, you need to move over. And so there is a possibility for, if it's really urgent and like really bad, they will use the fuel that's on board and move it over. Otherwise, because there's only so much fuel, they'll just let it run. And they'll just send the ephemeris information and say, hey, this is the compensation for where you were located. And they'll just send it that way. So it's not like it's going to move it over all the time, because you do run out of fuel. So now we're just going to just stay in position, and it's just going to stay where it is. And the ground control says, hey, change where you are, or change your code and tell us where you are actually. So the receiver clocks themselves, they're also cause of error. So they're definitely less accurate than the atomic clocks, which makes it more cost effective for us. But it causes errors because it's really hard to time them when you have a less accurate clock versus a very highly accurate clock. And so if we increase the number of satellites, we can estimate the error in the receiver clock, and then that makes it a little bit easier to adjust for that error. Then receiver noise. So we're getting close to the end here. There is receiver noise. The receivers have their own errors, right? So you have all kinds of radio frequencies that are around that can cause interference within the receiver. There's electronics in the receivers that's also going to cause an issue. And so the high quality receivers, if we have a really good one, the receiver noise is less than a millimeter, and then a few centimeters for the code phase. So there's different types of receivers. So we have carrier phase receivers and then code phase receivers. So again, those are for the higher accuracy ones, but your cell phone is a few centimeters for sure. So there's also other errors that we cannot correct, and we just say it's part of the random noise, and that's just kind of a component that gets thrown in there. So other things that can happen is the humans can add error. So errors, if you're not doing it right, can add error. Honestly, the estimated impact is anywhere between 1 to 200 meters. So as a user, you could put it in the wrong spot. It may not be totally above it. You might be using the wrong coordinate system. Your body might be in the way and causing signal degradation. The way that you've set it up, like for example, if you didn't put your handheld right above that spot, then you're going to be off. The other thing too is making sure that you are actually fully receiving all of the satellites. That is another error that we will often see. We call it fixed and float. Fixed means that it's receiving the full code. It now knows exactly where it is with respect to those satellites. And so it's being able to calculate its position. If you have a float situation, you're going to be off by a couple hundred meters, and it's not going to be able to correct for itself, and then you end up with an additional error with that. So in summary, the GPS errors, it goes through a lot of stuff. So we have atmospheric errors, we have multipath errors, satellite geometry, which is our DOP values. We have clock errors, we have orbit errors, we have receiver clock errors, we have receiver noise errors, and we have users. So there's lots and lots of errors with this. So when you go to do any kind of mapping with a GPS unit, you need to keep all of these in mind. So your placement, what you are picking up, what type of equipment you're going to use, all impact your final result. No required readings, no exercises. There's my references. And I look forward to Objective 2 with you guys.